Hello and welcome to another video in this series as together we learn the basics of Lean in order to write simple proofs. We are now well into part 3 of our kind of journey, and in part 3 we were going to practice using Mathlib's own definitions and lemmas. We started part 3 by using Mathlib's definition of odd and even numbers. We then started using some lemmas to help us write proofs. And then in the last couple of videos, we actually wrote our own lemma and then used it. Today we're going to write our own definition, which is actually a slightly simpler thing to do because we don't need to prove it. There's nothing to prove, it's just a definition. But it's a nice thing to be able to do and can be useful. So let's dive in. So we're going to actually be writing a definition of triangle numbers. So just a reminder, if you look at these pictures, you can see there's a progression, so 1 and then 1 plus 2 and 1 plus 2 plus 3 and 1 plus 2 plus 3 plus 4. So that's how the shape grows, and the triangle numbers are then the sums, so 1, 3, 6, 10 and so on. Although we're not going to prove it today, and it's a nice easy proof actually, it's quite fun if you want to look it up. The nth triangle number is n times n plus 1 over 2. And just as an aside, there's a nice interesting bit of math history or math mythology, I don't know if it's true. I think it was a young Gauss who, in school, the teacher wanted everyone to shut up and be occupied for a while. So the teacher set the class what he thought was a difficult challenge of adding up all the numbers, 1 to 100, so 1 plus 2 plus 3 and so on. And the story, whether it's true or not, says that Gauss came up with the answer really quickly. So instead of actually manually adding up all the numbers, he derived this kind of expression and then did it that way. The thing to note is when we were using the definition of odd and even, you remember the definition didn't return the nth odd number or the nth even number. It wasn't a function in that sense. So odd 3 wasn't the third odd number. It was a proposition, so odd 3 is either true or false. And that's kind of what we're going to do today. So just a reminder there. So odd 3 is a proposition which is true. Odd 4 is a proposition which is false. So supplying a number to odd returns a proposition which is true or false. So that's just a reminder of what we've covered before. So we want to do the same. We don't want to create a function which returns the nth triangle number. We want to create a definition which, when supplied with a number, is either true or false if that number is a triangle number or not. That's what we want to do. The way to think about the word proposition is it's a statement which can be true or false. So, 3 equals 2 plus 1 is a proposition. 3 equals 2 plus 2 is also a proposition, but it's false. So a proposition for us, for a triangle number, could be, remember it has to be true or false, so we have to be able to decide the truthiness of it. So there exists a number n, a natural number n, such that t can be expressed in the form n times n plus 1 over 2. Remember, that's the nth triangle number. So we're not saying it's the nth triangle number, we're saying if it can be written in this form, then it is a triangle number. So that proposition is only true if t is actually a triangle number. Let's draw a picture just to illustrate that, because this page looks a little bit dense. So our proposition is that there exists a natural number such that t can be written in the form n plus 1 over 2. So let's try that with 1. T equals 1. So can we write it in this form? I think we can. 1 equals 1 times 2 over 2, that's 1. So yes, we can, and therefore the proposition is true. So triangle 1 is true. Let's try it with another one. Change colour. Let's pick 6. So is it true? Is triangle 6? Is that a true proposition? Well, what does triangle mean? It means there exists a natural number such that 6 equals n times n plus 1 over 2. So there exists a natural number such that 6 can be written in the form n times n plus 1 over 2, which means we need to find an n. And it doesn't matter how we find it, as long as there is one that satisfies this condition. Can we do this? Let's say 3 times 4 over 2. 6 equals 3 times 4 over 2. That works. So yes, 6 is a triangle number. If we had 7, triangle 7, that wouldn't work because we can't write it in this form. So that's just to illustrate that. We want to just call out something here. So division is something we should be cautious about when working with natural numbers, because 4 divided by 2 is 2, that's a natural number, but 3, a natural number, divided by 2, a natural number, the result doesn't exist in the natural numbers. So we just have to be cautious. In this case it doesn't matter because n or n plus 1, at least one of those two, is an even number. So if that's, let me draw a picture. So n plus 1 over 2. So if n is even, then n plus 1, that's odd, over 2. Because that's even, then this divides nicely. But if that's not even, then n plus 1 must be even. So then that divides nicely. So in this case, it doesn't matter, but it's good habit anyway to avoid division by 2. So what would we do if we're trying to avoid division by 2? Well, let's start with the there exists an n, that's a natural number, such that t equals 2, n plus 1 over 2. Can we reformulate that so that we can avoid a division? We can. We can say there exists an n, that's a natural number, such that 2t can be written as n plus 1. So that's actually equivalent, but this definition just avoids the division. So if we're testing 6, here we're saying 6 equals, I don't know, 3 times 4 over 2. Whereas if we're testing 6 here, we have to do 2t. So we then say 2 times 6, which is 12, equals 3 times 4. So that works. So 2 times 6, which is being tested, can be written as n plus 1. We can 3 times 4. So this is just the equivalent version, and it's avoided the division by 2. It's just a good habit to get into if you can do that. Great. So we'll look at some code and we'll talk through it actually with a kind of live editor. The last 3 times we used the online web environment. Today let's use the Visual Studio one, just for a bit of variety. So we import Mathlib as usual, mathlib.tactic, and you can see here we're using def, and that kind of gives a clue as to what's happening. This is a definition. So remember when we had simple proofs that we weren't going to use again, we had example, but then when we had lemmas that we were going to define, we'd have a lemma and then a name of the lemma and then the rest of it. Theorems would be the same. As we said before, in Mathlib there isn't a clear distinction between the two. So here, fairly intuitively, def means we're about to define something, a definition, give it a name, call it triangle. We've got some variables that we want to declare. And remember, the round brackets means that whenever this is used, the variable has to be supplied. It's the same thing with the lemmas. And then we have a prop which says that the type of this thing called triangle, the thing that we're defining, has a type proposition. And then we go into the detail of what that actually entails. So this is familiar. There exists an n, a natural number n, such that, I should have put, there you go. There exists a natural number n such that 2 times a, actually there's an interesting point there. If I didn't define the type of the natural number, if it was, if I didn't say it was, a rational number or a integer, the assumption is that it's, see, if I hover over it, it says it's a natural number. But for completeness, it's a good thing to be able to do that, just to be clear. So that was a good spot. So we're saying there exists a natural number n such that 2 times a being the parameter that's supplied, 2 times a can be written as n times n plus 1. So there's an existence statement. Remember, we've done existence previously, and remember how to prove them. We don't really mind how you come up with an example. All we have to do is show the example works. So we'll practice that in a minute. So that's it. That's all there is to this definition. So there's not a lot new. There's lots of familiarity. Def means we're about to do definition, a name, the variables. What's new is that we've got a type here, which is called prop, and we've not seen that before. So prop just means it's a proposition. What proposition? Well, there's the detail. We'll talk a little bit more about prop later today in this video. We'll pause that for now. So that's the definition. One line, done. Most definitions will be one line, but not always. Great. So how do we use this? It's always a good idea to provide a minimal example to illustrate using your lemmas or your definitions. So here's a minimal example, which is to prove that 10 is indeed a triangle number. So we've defined this. Sorry, we've made a proposition, triangle 10. That's a proposition. Remember, it's not the 10th triangle number. This should be read as 10 is a triangle number. Let's unfold that. So remember using dsimp with, we used to use odd before. We can say triangle, and that should, so if I put my cursor before, my proof goal here is triangle 10. Once this is executed, I'll place my cursor at the end. You can see it's unfolded into its actual definition. There exists an n such that 20, remember it's 2 times the number, 2 times a, 2 times 10, 20 can be written as n times n plus 1 because we wanted to avoid division by 2. That's our proof goal. So to prove 10 is a triangle number, we need to prove there exists an n such that 20 can be written in this form. And we can probably do that in our heads. Remember, with existence proofs, it doesn't really matter how you come up with the example, you just have to show it works. So if I say n is 4, 4 times 5 is 20. So if I say use 4, that completes a proof. Nice and easy, simple. So there wasn't actually a lot to that, but it's good to see a simple example of a definition being created. Great. So let's see if there's anything else we wanted to say. All these slides are online if you want to read them in your own time. This is just a picture showing that structure, similar to how we had a similar picture for writing proof headers. This is def, then the name, variables, type, and the definition. We'll talk about prop in a minute. We did the simple example, which was very simple. And we had a look at the info view. We've already done that, as we said. So just here, before dsimp, the goal is written in the form triangle 10. And by using dsimp, we can unfold that into its definition, into the detail of the definition. That can be useful sometimes. It's not actually necessary, the proof still works without it, but it can be helpful to understand, well, what are you trying to actually prove? So all of that is just revision. Great, so let's talk a little bit about terms and types and props and things like that. Now this is an optional section, so you don't really need to know it in order to use Lean to write simple maths proofs, but it can give you an extra insight into what's happening. So let's compare these two definitions. Triangle is the one we've just done, and here's one I've just made up, triple a number. You can see they both start with def and then the name, and then the variable types. So a is a natural number and a is a natural number here as well. In the triple, the type is the output type, I guess, is a natural number, and the detail is 3 times a. So if I say triple 3, I should get 9. So this is the type of the output. So the output of this is a natural number. So you can think of this as a standard function in the way that we learnt about them in school. We provide 3, an a, it triples it and gives us the output. So the output type, return type, is natural number. Here the return type is not. Remember we said triangle doesn't give us the nth triangle number, it just gives us a proposition which is true or false about that number. So that's a proposition, that's a type which you may not have come across before, in the same way that that's a type. We will draw some pictures to explain that. I realise this is new. So some terminology here. The type of triangle is proposition. The type of triple is natural numbers, the set of natural numbers. So the output's a natural number. Let's draw a picture of that. So triangle and what was the other one? It was triple. And this one, the output type is prop. And the output type of this is natural number. Which natural number? 3 times a, and a is the supplied parameter. What proposition? Well, in this case, it's there exists an n such that 2 times a equals n plus 1. So this is the content of the output proposition, and the type of the output is proposition. This is the content of the output, which is of type natural number. So that's just a comparison there, so you can see what's going on. Now, that may or may not be surprising, that proposition as a type. Some people find that difficult to accept, some people don't. Some more terminology. So that detail in the triangle definition is called a term of type prop. So that's a term. And here the term, 3 times a, is a term of type natural number. So there's a hierarchy there. Let's look at a picture. So in Lean and Mathlib, this picture is a simplified form of most objects. As I say, you don't need to know this, but it might be of interest. So right at the top you've got universes, the biggest kind of category, I guess. You have types. This is confusing, we're using types twice here. So there's types and props. In the universe of types, you might have sets. So natural numbers, complex numbers, integers, and so on. So the natural numbers is a set, and it is a type. And within those sets, you might have elements like 13. So 13 is a term of type natural numbers. Similarly, in the other part of this picture, in the universe of propositions. We have propositions, and an example is odd 13, or triangle 6, or triangle 7, which is a false proposition. The true propositions might have proofs. Now this is the bit that surprises new people. Surprised me for sure, in a pleasant way, but it's definitely a surprise. In the same way, 13 is an element or a term of type natural number n. Proofs are an element, are a term of type of propositions. That's interesting, isn't it? So we're saying a proposition 13, there are proofs that belong to that thing called a proposition. And there could be multiple proofs actually that belong to that, just in the same way that 13, 14, 15 are elements of the natural numbers. I can have different proofs of odd 13, but they are kind of, they belong to it in that sense. There is ownership relationship there. That's interesting. So just to introduce some terminology, as I say, there's no rush to let this sink in. For most people, including myself, it takes a while to get used to this idea. But the more you see, read and write lean code, you'll start spotting these in the code that you're reading and writing, and it'll just give you that extra layer of understanding. I actually think it's quite exciting, this idea of having propositions and then having proofs that are members or elements of that proposition. I think that's quite interesting. So let's talk about a simple, easy exercise. We say easy, we don't mean to be patronizing. The idea is not to have difficult maths, so we can just focus on practicing lean. So we've just created a definition of triangle numbers, and we had a quick look at a definition of triple as well. What we want to do here is write a definition of square numbers and call it square. And in the same way that it won't be something that returns the nth square, we want it to be a proposition that's true or false if the given number is a square number. It can be written in the form n squared. So if you write that definition, it shouldn't be difficult. It should, you can take the code we've got for the triangle numbers, then modify it, and then write a small minimal example to show that 25 is a square number. So let's have a think about how we might do that, just to give you some hints. So we probably have def and then a name, which we'll call square. We want a parameter to be passed to it, otherwise we don't know which number we're talking about. Let's call it a, which is going to be a natural number. And what we're returning is not a number, not the nth square, but a prop, just like we've done before, a proposition. And then I'll leave you to fill that in. I won't do it all for you. And then to show that 25, we might have example, and then say, well, we don't need any parameters. We can just jump straight to the proof objective, which is square 25 by, and then you can probably use dsimp square to show in the info view what the actual definition details are, and it hopefully is a there exists statement, in which case you can probably use some number here. Should be something like that. So have a go. Any problems or any questions, do comment and we'll have a discussion. But I hope that was short but sweet, an interesting tutorial today. Next time we'll use the definition of triple to prove a slightly more involved theorem. So that should be quite fun. We're looking forward to that. Cheers. Bye.